Hi, everyone, and thanks for joining the third session for our Bayesian seminar series. As usual, here are the important links, and feel free to share them. So a quick reminder, we'll be hosting our workshop on post-Bayesian method at UCL in London this May. So registration is open, and we are accepting a submission for contributed talks and posters. So here's the QR code with more information if you are interested on the workshop. As always, we will be using the Q&A function in Zoom for questions during the talks. So please use the Q&A rather than the chat. And Jan and I will be monitoring them and ask the speaker during the breaks or during the talk when we think is useful. So today we will continue with chapter 1. So here's a quick reminder of this structure. And today we are honored to have Professor Ryan Martin with us. He's a professor at North Carolina State University, where his research focuses on the theoretical foundation of statistical inference and has with significant contribution to inferential models and representative quantification. Ryan will talk about learning rate selection and its connection to our posterior, and his work has been instrumental in advancing our understanding of learning rates, particularly their role in calibrating the posteriors. I'm really excited for this talk, so I'll hand it over to Ryan.
Okay, let's see. All right, that looks okay?
Yep.
Okay, well, great. Yeah, thanks so much for the invitation for sure, and a nice introduction. And yeah, it's great to see a good crowd here interested to learn about generalized Bayes sorts of things. This is something I've been working on for, I guess, a number of years now. And so what I want to present here will be kind of like touching on a few things over, I guess, just thinking of it now, maybe close to 8-10 years of work kind of thinking about these sorts of things. So yeah, very happy to be here, and if there's questions during the time, of course, feel free to jump to Matthias, you can yell out, and I'll try to answer those things. My website is there in case I forget. If you want to reach out to contact me, you can find my email there, or like links to papers and stuff like that. And also this slides, I think that will be made available on the seminar website, but I'll also put those up on my website as well. All right, so let's get but just to make sure we're all on the same terms of notation stuff. So the setup here is like this: there's something that's unknown that we want to learn about. So call this quantity of interest theta, and then we get data, right? And so this data is carrying some relevant information about that unknown. And so what is our goal? Our goal is to flip this into some kind of like uncertainty quantification about the unknown given the data that we observed. All right, so of course the Bayesian inference is one way that you can handle this, but as we know, and I guess that's largely the motivation for okay, the sound is all right. Okay, I see there's some okay. Okay, so I guess one of the motivations for this seminar series is that, well, there's some obstacles in actually carrying out the sort of familiar Bayesian inference. And so, model misspecification is one of them. I'll talk here just in a moment about model under-specification, prior choice, maybe a variety of other things. And so, again, this seminar is really designed to talk about ways of overcoming these obstacles. I didn't know where was exactly the right place to insert this explanation, but I wanted to do it before people fall asleep, so I will do it right at the beginning here. This is I guess, to try to emphasize that at least my thinking about the Gibbs posteriors and generalized Bayes more specifically is like beyond the kind of correcting for model misspecification. And so I really like this line here from Wasserman, kind of hinting at this kind of idea about essentially interested in trying to liberate the kind of the usual Bayesian type of construction. And so I'd say this under-specification notion is underappreciated. What I mean by this is that this theta that I'm writing here, even though it's a Greek letter and we like to think of Greek letters as parameters of models, often this thing is not a quantity that determines a model. Right. And so examples of this would include things like quantiles or this MCID, which I'll describe. In machine learning problems, often the estimand is not something that we would naturally think of as a model parameter. Right. And so if you're wanting to follow the usual Bayesian program, what they need is a model. Right? A Bayesian formulation needs a model. And so if you go in this route, right, what you end up doing is you're kind of building up a model that embeds the actual problem of interest in it, right? And so when you add on these extra layers, you're creating some kind of risk for model misspecification bias. You're introducing nuisance parameters that you ultimately need to marginalize out. This also creates challenges in terms of like specifying priors, right? Because this higher level model that you introduce involves parameters that don't mean anything, right? And so naturally, you're not going to be able to write down meaningful or informative type of prior distributions for things that don't mean anything, right? And so if we're able to focus just on the things that mean something, that creates opportunities for actually using informative priors, which is what's going to help Bayesian inference kind of outperform other kinds of procedures. So I think that this generalized Bayes and Gibbs posteriors and these sorts of things, this is bigger than just accommodating misspecification. So I have my sort of summary of my perspective of kind of related to what Wasserman's saying here is that this generalized Bayes, you could think of this as sort of a liberated Bayes. Okay, so now into, I guess, some specifics, some notation and stuff. So I'm going to treat here data IID, let's say it's Z1 to Zn is packed inside of this Z superscript n. There's some underlying distribution P that's unknown. The main ingredient here is a loss function. And so this loss function takes as input a data value and a parameter value. And so what gives this some kind of connection to the real problem is that quantity that we're interested in is the minimizer of this risk. And risk, remember, is like a expected loss. Okay. And so what we're interested in is, again, is this inference about this risk minimizer. And so that's specifically what Gibbs posterior is designed to do. So here is the form in this sort of brief kind of equation here. We've seen this in the previous week's presentations. My notation is maybe a little bit different here, but what this is doing is just taking prior distribution and updating it using this packed inside of this R as the loss function. And that's here in this empirical risk, right? Just averaging the loss values over the observations. Okay. So now the thing that stands out here, I highlighted it in a red color, is this omega term. And that omega term is the thing that's called the learning rate. And so this learning rate is the main topic of the presentation here. And so here is roughly what I want to say in the presentation. So give a little bit of background about the Gibbs posteriors, their motivation, and kind of how this comes to be. A bit about the posterior concentration, kind of a review, a little bit of what David talked about last time. This is mainly just to, as it connects to these questions about the learning rate. And I'll talk a bit about some of the existing learning rate selection methods, the calibration, and then I guess it's the specific proposal that my former student and I put forward. There'll be some illustrations and examples, comparisons of the different learning rate selection methods along the way. Depending on the time, it's not so important if we have time for this or not, but a couple of things that I could maybe comment on. So one of them is related to prediction. The other one is completely off topic in some sense, is about some recent developments in things called anytime valid inference. So I guess we'll see how we do in terms of time. So in the slides, I don't really give like comprehensive references. Well, it's just a matter of taste, I suppose. But so most of what I'm going to say is in this review paper from a couple years back. This is published in a Handbook of Statistics. And so really addressing a lot of these points about the Gibbs posterior and the properties that it has in terms of like the posterior concentration and how to achieve this kind of calibration through the choice of learning rates. So how I got interested in Gibbs posteriors in the first place. So I call this here, this is the example that was my motivation. This was a seminar presentation given by one of my then colleagues. And so it was talking about this very applied type of problem. And so the question was about, I guess, the basic question there was like, how do you know if patients feel like a treatment was effective? Right, so we learn a lot about, in statistics about judging whether a treatment was effective statistically, right? But this is about kind of this balance between a practical and a statistical significance. And so trying to get at what is some kind of like a threshold beyond which, on some kind of like a diagnostic measure scale, beyond that threshold, do the patients feel like the treatment was effective, like they feel better? Okay. And so the setup here is like data comes in pairs, and there's a real valued kind of diagnostic measure and then a binary indicator whether the patient felt like the treatment was effective. Um, and so you can think of it this way: is like X is kind of like think of it as like a test statistic. And if that test statistic is too large, then we would make a judgment that the treatment was statistically significant. And so this X is kind of like on a standard statistical type of scale, and then we want to relate that X on a statistical scale to how does the patient feel? So there's this quantity here that's called the minimum clinically important difference, or MCID. This is just a risk minimizer. And so the particular risk is this essentially like a misclassification error, right? So it's looking at is that diagnostic measure exceeds this threshold. If it does, then we would want the Y to be +1. If it falls below the threshold, then we want the Y to be -1. And so it's thinking about how do you kind of balance these kind of things. So anyways, there is a risk function that's there. And yeah, I think I already said that this is the MCID is like the X scale at which beyond which the patients would feel like the treatment was effective. So what does this have to do with the Gibbs posteriors? Well, I was thinking that when I heard this presentation, I thought, well, seems like something you could do pretty easily in a Bayesian kind of way and bring in, for example, something like logistic regression or some other kind of like fancier binary regression to deal with this problem. And so just was interested to see if I could do it. And what ended up happening was that tried a few of these things, some basic logistic regression and some fancier non-parametric version. And I was seeing things like in these two pictures is that there's some sort of quote good cases where the dashed and dotted lines are these logistic and binary type of model fits. And so what was happening here is that these are, in some cases, were good, and they were all kind of concentrating around the right thing. Right? Vertical line here is the sort of the right thing. And then there were other cases, what I'm calling here bad cases, where there seemed to be some kind of bias. And so those logistic regression and fancier kind of non-parametric binary regression were pushed off target. And the difference between the good and the bad ones were almost indiscernible, right? So like very similar type of models you're generating data from, and you can't expect that you'd be able to tell based just on observed data whether you're in a good case or a bad case. But what happened was that I tried this Gibbs thing, and so here I'm not dealing with the learn rate at all. But the point is that in both the good and the bad cases, it's pointing right at the right thing. Right. So it seemed like this seemed quite promising, and I remember feeling like what I thought was supposed to be a pretty straightforward problem couldn't be resolved with these kind of standard techniques. And I thought, well, maybe this Gibbs posterior, there's something there, right? That this is some way to kind of avoid having to address this question of whether I'm in a good case or bad case and then respond accordingly. All right, so this was my motivation to get into Gibbs posteriors was this MCID problem. Now, we've seen in some of the previous lectures what I'm presenting here on this slide, but just again to make sure that we're on the same page. So this like decision theoretic sort of formulation of the Gibbs posterior goes something like this: is that there's kind of a optimization problem that involves two terms, right? There's a term that's kind of saying, okay, how close should we chase the data? Then there's another term saying, well, how close should we stay near the prior? And then there's this kind of balancing act, and then you pick the one, this like posterior distribution that minimizes this kind of weighted sum, right? And so inside of here, there's that omega term, that learning rate, and that's the thing that we ultimately are going to be interested in making some choices about. Right, but of course we know that the solution to that optimization problem is just to basically use Bayes' rule, but with a fake likelihood. And so then that fake likelihood is just this thing here. This has the empirical risk inside this Rn. Okay. And so what's going on here is this omega is kind of controlling the rate at which the information about the parameter in the data is accumulating relative to the information about theta in the prior distribution. And so we can't get around this specific, dealing with this learning rate, because the problem itself doesn't come with a sort of meaningful scale on the loss function. Right? And so to that point, um, well, there's a mathematical, I think, mathematical way that you can treat this. I guess I like to think that there's something kind of practical going on here. Is that when we write down these loss functions that we use for carrying out these inference, usually we pick those loss functions not because their like numerical values are actually representative of losses that are suffered. It's that we like the shape of the particular loss function, and so things like we want the minimizer to correspond to an expectation. Things like these are the things that we have in mind when we're choosing these loss functions, right? Squared error loss isn't popular because that's how much loss we actually suffer. It's because that's the shape that seems that's pretty natural, right? And so in this context, the ordinary loss and a loss that's scaled by some omega, those are exactly the same thing. And so we can't really distinguish between those. And so we have to work with this kind of like equivalence class of losses. And that's where the need for addressing this learning rate comes. Right? This doesn't show up when we are just dealing with M estimation because all that M estimation cares about is the shape of the loss. Right. So you're trying to minimize the loss function, or minimize the expected loss. So the shape or the scale obviously doesn't matter. When you try to do inference, you get this like sandwich covariance matrix, and that has a ratio of the losses, and so it cancels out this effect. Right. So we don't ever have to deal with this like scale ambiguity if we're just talking about M estimation, but we do have to deal with this in other cases when we're dealing with, say, Gibbs posteriors. Okay. So another point that's, I guess, not immediately clear maybe is that we can't just treat this learning rate as an ordinary model parameter and just estimate it, right? And so the reason is that things like H Bayes, hierarchical Bayes, this kind of thing works when you have a model that ties the data and the parameters all together, right? But we're specifically here thinking not about cases where we have a model that ties everything together, right? So the data themselves are not going to be directly informative about this learning rate parameter, right? And you can think of it as that, even back into this previous point, is that the learning rate might be showing up because there's not a meaningful scale on the loss function itself. The data can't possibly know about that. Right. So there just isn't information in the data directly about the omega that we could use to say form a likelihood function, maximize, or introduce a prior, and then expect to learn through this kind of updating process. Right. So we need some other kind of ways to proceed with this. So there is a this I guess I'm considering this here kind of like a special or an edge case is the situation where we have a misspecified model. And so again, we've seen this already in the previous lectures, but it's worth to mention again is that one way that this can come about is that I actually go through the trouble, I construct some kind of model that has some distribution p theta, and maybe there's a density function little p theta corresponding to this. And so in this case, I can fit this within the Gibbs framework just by introducing a loss function that's just the negative log of the density. Right. And so in this particular case, then there's the risk function is connected to a KL divergence. And then we understand this like sort of true parameter that we're trying to estimate. It's not really true. It's just this one that's the KL best within the posited model. Right. So you could think of kind of a projection of the true distribution onto the model space. And then that's the sort of the quote truth. Okay. So even in this case, right, if I go to all the trouble of having like an actual model density function, there's still some scaling ambiguity because that model's not right. And so the data getting plugged into this and forming a likelihood function is not really an adequate, or it's not properly scaled with the prior distributions and so forth. So there's still this ambiguity, and so still a learning rate that needs to be dealt with. So even though when you follow in this kind of framework, right, you end up with a thing that's like a likelihood function is actually a real likelihood function, but when we have the learning rate there, it goes to a power. So sometimes this is called a power posterior. But I want to go back to that point I made earlier on, is that Gibbs and misspecified Bayes are not the same thing. So I think the way I want to summarize it here is that, on the one hand, you can be thinking like I do misspecification on purpose, right? And misspecification on purpose means, for example, I don't even try to do modeling, right? I just use directly a loss function that connects the quantity of interest to data. Or I might cheat and say, well, how about I just specify a model that's overly simple, for computational reasons or for other sorts of reasons, and then hope that I can still do a good job with that simple model cheating. Versus I actually try my best to do the modeling, and then I just happen to get it wrong on accident. Right. These are things that I think these are very different situations and sort of epistemic states. And so, for example, the person who does the misspecification on purpose probably isn't willing to bring in the learning rate because that means they had to admit that they did it wrong. Right. So it's really only in this kind of context where we're acknowledging that there is a potential model misspecification, which brings it in more into this kind of like a Gibbs framework versus a misspecified Bayes framework. So there's a tendency, so I get this when I sometimes talk to people about these problems, is that there's a feeling that this is just, you're just dealing with Bayes, but with a misspecified model. And I think there's more to it than that because we might actually be doing the misspecification on purpose versus misspecification on accident. All right, so then, before we can get to some things about the how do we specify this learning rate, it makes sense to sort of see, okay, what is this Gibbs posterior doing? And this is, again, just some kind of review from things that we've heard in previous lectures. But the basic intuition is that the Gibbs posterior density itself is going to be maximized near where the empirical risk is minimized. And the empirical risk, of course, is going to converge to the actual risk, at least point-wise, right? So there's some issues maybe about the uniformity or whatever, but just at the high intuitive level, this is what's going on. And then, of course, the empirical risk is defined to be minimized at, or sorry, the real risk is defined to be minimized at the true theta. And so then really the only thing that can possibly happen is if it's concentrated anywhere, it has to be at this truth, right? So it is going to be pointing in the right direction. We don't know anything about kind of the spread, but at least in terms of like where the mode is, for example, that's going to be pointed in roughly the right direction. All right, so there's lots more to say about this, and I'm just giving this sort of high-level type of overview here. But so David's talk from the previous lecture talked about a bunch of these things in much more detail, and I think that you should refer to that, not listen to what I'm saying about this here. Just as a kind of an example that you can formalize an intuition. So I don't claim that this is in any sense is the best possible result, but this was one that I had. It was essentially, this was my intuition kind of as I was starting to think about this problem, 8 some years ago, was like, well, what would it take for us to have this kind of like a Gibbs posterior consistency? And my intuition was that if we can get consistency of the M estimator and some kind of like a prior concentration conditions, then this ought to hold no problem. And so it's not just about consistency of the M estimator. It has to do with the kind of conditions that lead to consistency of the M estimator. But effectively, this is let's say effectively my intuition was right. And so this was this result appears in that review paper that I mentioned at the beginning. Okay, so of course, concentration is nice. That's not the whole story. And so this again will be related to the learning rate choice, is that you can say a bit more about the concentration of this Gibbs posterior if you have some more regularity. So in this particular case, what's of primary relevance is like that risk function being smooth at the truth, at the minimizer. And so the smoothness that we need is that this second derivative is non-negative there. Positive there. And so then roughly what does this like asymptotic normality or Bernstein-von Mises theorem say? Says that Gibbs posterior is going to be centered around the thing you're trying to target. That's the concentration part. But moreover, it's going to look like kind of Gaussian, and it'll have an asymptotic variance that looks like this, right? So it's like the inverse of that second derivative matrix, but scaled by the learning rate. Okay. So the learning rate shows up in the limit, right? So in the concentration part, it doesn't show up, right? Because that's just saying what's kind of, it doesn't say anything about the shape. It's just about where is it concentrating. But as you zoom in a bit more and look at the shape, then the learning rate, of course, plays a role. The reason why we have to care about the learning rate is that, at least in terms of calibration type of considerations, which I'll talk about shortly, is that you get this kind of covariance mismatch, is that the M estimator or the posterior mean, whatever, it's going to have an asymptotic variance that looks like this thing on the left. But then the Gibbs posterior ends up having variance that looks like the thing on the right. And those are generally different. So you get this kind of like a covariance variance mismatch. And so if you were to ignore the learning rate entirely, or just say like just call it equal to one, and I don't bother with it at all, then you could have very bad uncertainty quantification because these could not be matched up at all, right? Could be entirely different, and you could get, for example, credible sets that have virtually zero coverage probability, things like this. And so that I think is potentially problematic, and that reveals itself in this large sample theory. Okay, so while dealing with this learning rate might be annoying, I say here, I view this as like we have an opportunity to make a correction if necessary. Is that if we were just doing ordinary Bayes without learning rate or not thinking about that, we just get what we get, and there's nothing we can do to correct it. But at least in this case, if we recognize this mismatch, we have something that we can play with, this omega, to possibly make the adjustment so that it's not a disaster, right? We can do something to try to make some degree of correction. Okay, so now I guess into the more, I guess the main part of the talk, which is about this learning rate choice. I would say that, so, except that none of these methods try to estimate the omega as if it's a model parameter. These are entirely different. And so here is I guess, a non-exhaustive list of things. These are the ones I'm familiar with. Maybe there's some others that I'm not aware of. So I put here just a snippet to kind of see, okay, like how are these, what's the spirit of these different kinds of choices? And so Grunwald's safe Bayes, this is defined to be something like this. It's saying construct a type of accumulative posterior risk and then choose the learning rate to minimize this. Right. So obviously minimizing a type of risk makes sense, right? There's some desirable benefits there. This leads in turn to certain kinds of risk control. So this is like so I think several folks have shown this plots for in a regression context to see like the kind of path of these risks as a function of the learning rate, and by making certain choices in terms of the say this minimizing cumulative posterior risk, they're able to keep this risk low, whereas other Bayesian solutions are having a high risk there. The Holmes and Walker does something entirely different. So this one is trying to do some kind of like a matching of information in data and information in prior. And so this information in data necessarily brings in some considerations about the loss function. And so then different loss functions have different information, and then you're trying to do this kind of a matching. So a very natural way to proceed, but of course very different from what Grunwald's suggestion in terms of minimizing some kind of posterior risk. Another work is Leiden, Holmes, and Walker. This was 2019, I believe. So they're similar in spirit to this information matching, but using a different strategy to get there. So some kind of like a bootstrap type of procedure. This one ultimately is, well, I guess has various justifications, but one of them is that asymptotically there's some degree of calibration. The last one here in the list is, again, very different from the other three, is where calibration is the specific target, and then carried out some kind of construction of a bootstrap type procedure to directly hit this calibration priority. So I'll say a little bit more about the last one in a second, some more details. But none of these can be considered right. So basically, there is no such thing as the right choice of the learning rate. There are just different priorities and tastes and opinions. So just as an example, so this was I was thinking about this earlier. So this is probably 2015, 2016. I was sitting with Stephen Walker. We were having a beer, and I was telling him about, I had this idea for bootstrap type of procedure to target like calibration of these Gibbs posteriors. And I don't remember exactly what he said, but I left that meeting thinking that, well, Stephen thinks that's a really dumb idea. And well, dumb or not, I guess that's I don't know if I can speak to that, but anyways, so maybe he thought that my idea was dumb, and then I thought it was not dumb, right? So these are things that maybe there's just some different kind of tastes. But since this is my talk, I get to talk about my idea. So that's what I wanted to do next here. All right. So I think there's a key idea here, and this is thinking about what are the priorities that we would like to as we're considering different type of learning rate choices, what are our priorities? So for me, I was thinking about things in terms of calibration, and this has to do with I think of this as kind of more fundamental type of foundational type of consideration. And so there's a line here from Don Fraser, I think 2014 paper. So this wasn't specifically about Gibbs posteriors or anything like this, but I think it applies maybe more so for Gibbs posteriors than any other. Is that you can't expect that just by applying something like Bayes' formula you can turn probabilities that are fake into probabilities that are real. That just isn't going to happen. But the good thing is that we don't need the probabilities to be real for them to be useful. And so since as you, I don't consider myself old, but I guess as you start to get older, you think, okay, well, why are we doing the certain things that we're doing? So when we, many of us are concerned with these kind of things like calibration or reliability, not because we necessarily think of it from a philosophical point of view, but because we're in the business of developing some kind of methods and software to go along with this, and we want people to use those things. And you say, well, why would someone use these things that I developed? Right? I don't know anything about their problem, so why would they trust me with answering their questions? And so the only explanation I can think of is that, well, you'll use my method, or I'll use your method, whichever, if I can prove to you that it's going to work, right? Going to give you the right answer. And so for this, we need some kind of way of since we're dealing with probabilistic type of inferences like these Gibbs posteriors, what we need is some kind of calibration of those posterior probabilities. And so I guess in a sentence here, what I mean by this is that we want our posterior to assign low and high probability to the true and the false hypotheses. Right. And so that I think is roughly what Fraser is kind of getting at here, is that maybe they're not going to be real, but at least they're reliable in some way. Okay, so to formalize this a little bit, what I wanted to say next is, I guess, to define what I mean by calibration here. So thinking about the credible regions that are drawn from this, that are constructed from the Gibbs posterior. So these will naturally depend on the data, this credibility level, and also the learning rate parameter. Okay. So what we would like is for these credible regions to also be confidence regions. And if they are, or at least approximately, then we can say that the Gibbs posterior is calibrated. So in terms of the actual formulation of what do we mean by this, is that it's just evaluate the coverage probability, and we want the coverage probability to match the credibility level, right? So I've got a function here. This is just the coverage probability function. I'm using here this, maybe it's a kind of weird notation, but this is just to say that the thing I'm trying to estimate is a functional of the true distribution. So whatever that functional is, we're talking here about risk minimizers, but anyways, it's some kind of feature of the distribution in question. All right, so then the goal is to solve this equation. Right, you can ask, okay, does the solution even exist? This is not so, kind of hand wavy here, but just to make sure that there's not really a serious concern about this, is that remember what the asymptotic results are saying. So whether this is asymptotic or not, at least it gives us some guidance, is that it's going to be concentrated around the truth, right? And then we can also see that as you decrease the learning rate, you get more spread, right? The data has less influence, so you get kind of a more diffuse type of posterior. And as you increase, it gets more concentrated, right? So there is this kind of fluctuation from being really diffuse, where the coverage probability would be large, to being very tight, where the coverage probability would be high or low, right? The other way. So that there is a kind of monotonicity in this coverage probability function as you vary the learning rate. So no real reason to doubt that there's going to be a solution to this. You can dig in, it's a little bit easier if you get into this kind of like near asymptotics, where you can use the Bernstein-von Mises theorem, that asymptotic normality. And there you can see exactly how the variance depends on the learning rate and be a little bit more precise. It's not very interesting calculation, but it's just that to kind of see that, okay, indeed, there is a solution to this equation that we're targeting. Okay. And so, suppose we were in this sort of magical situation where we actually knew what the true distribution was. right, then this would not be difficult to do. And I mean, this is actually not a bad exercise to do to kind of think about, do I understand how to find this learning rate or to understand what it's doing? Is that you can actually simulate from the true distribution and use Monte Carlo in this like a stochastic gradient descent or Robinson-Monroe type of strategy to actually solve the equation. All right, so here is the procedure how it goes, but I mean, it's pretty straightforward. Is you just generate new data sets from the true distribution, approximate the coverage using Monte Carlo, and then update the learning rate depending on whether you've overcovered or undercovered. Right. Right. Now that's not realistic. Right. So if you don't know the true distribution, which we never do, what can we do? So what we thought was, how about you just replace the true distribution with the empirical distribution? Right, very natural way to go. This turns it into something kind of like a bootstrap approximation of the coverage probability. But anyways, we just repeat the same steps. It's just now wherever you saw the true P, you drop in the empirical distribution. And so this, I think, is taking what is a sort of the obvious thing to do if you knew what the true distribution was, and then then if you don't know what the true distribution is, you just mimic that obvious thing, but with the first thought about what you can plug in as a replacement for the true distribution. Okay. Now, granted, this is not cheap. And so, I mean, that was never wasn't my top priority at the time. I just wanted to know, like, could we actually do this? While it's not cheap, it's also it's not too expensive to do. So my computational skills are not particularly strong. So I'm able to do this and I can get reasonable answers. So I fully expect that people with more talent in the computational side can come up with something much better. But I found that at least in some moderately challenging problems, this is quite easy to do and doesn't take too long. Basically, it's just that there's not really any payoff to having huge bootstrap sample sizes or tight type of convergence criteria. That just doesn't help. And so you can keep these at moderate levels and still get just as good as if you had very large sample size or very tight convergence criteria. So just as a quick, I mean, I like this one because it's a simple problem, but you can see sort of exactly what's going on with with this choice here is that it's a Gaussian process type of model. So there's some kind of dependence inside of the model itself, but it only depends on two parameters here. So there's a few things that you could do. One is just a full Bayes posterior. I forget what the prior distributions are, but it's not so important. There is just a full posterior you can do, MCMC, and I mean, it works fine. It's a little bit computationally demanding because there's large matrices you have to invert because of the dependence inside of the Gaussian process. And so to avoid those expensive computations, one strategy that's been proposed is to do a composite Bayes posterior, which effectively ignores some of the dependence. So now you're working instead of with a big matrix, you have to invert something with like a narrow kind of band. And so then that's an easier computational problem to invert such matrices. But ignoring dependence makes it so that you think the data is more informative than it really is. Right. So then you're going to expect that this kind of purposely misspecified posterior distribution isn't going to give you reliable uncertainty quantification. So what you could do is you could take this composite Bayes posterior, which you know is wrong, and try to correct it using, say, this calibration procedure. So what you see in this picture, maybe look at the joint distribution first. Black is the full Bayes posterior. That's the quote right answer. The composite Bayes is giving you this really narrow one in the middle. It's too concentrated because you've kind of over-exaggerated the informativeness of data. And then the gray in the background is when we do the calibration, right? So we've taken the gray on the inside and we've adjusted it so that it's now spread out a bit more and more realistic in terms of the calibration type of properties because, right, so you can see that the gray is kind of in the background is spreading out just enough to kind of cover the black cloud. Right. And so what you can see in the two marginal pictures here is that on the mu margin, we're actually picking up the posterior virtually exactly. This is the solid black line here corresponds to these black points there. And so that's, I guess I would say, quote, the right answer. So everything on the mu margin is looking great. On the tau margin, what we end up picking up is something a bit more diffuse than the Bayes posterior. but it is also right or reliable. I think I want to pick up the pace a little bit. So this is essentially the same kind of picture, just kind of comparing confidence regions versus the Gibbs posterior credible regions. And so the point here is that they're matching up very closely. I had mentioned about this kind of Oracle version of this calibration algorithm, and then there's the real one that uses the empirical distribution. So you could ask, like, do they line up? Like, do they give similar type of answers? They should. And so it's just a, relatively simple kind of comparison. And you can see here is that the red line corresponds to kind of the as if you knew what the true distribution was and you carried out the calibration algorithm, this is what you get. And then the box plots correspond to across different data sets using the empirical distribution. What do you get? And so, of course, it's going to fluctuate around this Oracle solution, but the nice thing is that it is following it. And so, as expected, giving the answers that we would want, kind of indicating that the plugging in the empirical distribution isn't disturbing this Oracle procedure too much. That it does actually achieve the calibration that we want is, I guess, also a question. And so it's not super important, all of these, the numbers here, but what we're trying to get is 95% intervals. And so this calibration algorithm is giving us 95% intervals. This is not asymptotic. It's doing it whether the sample size is relatively large or relatively large or relatively small, and doing so in a relatively efficient way. It's not achieving this by giving very large intervals, for example. So in terms of comparisons, so those other three learning rate choice methods, those are not designed specifically for calibration. They're designed for something else. It doesn't mean they can't be calibrated. It just, that wasn't what they were primarily designed for. So you can ask, okay, well, what if we do some kind of examples and we see, okay, can we check, do these other learning rate choice methods, do they actually achieve this calibration? And so here is one picture, and this is, I don't have a lot of detail on here, but this is basically a toy problem. It's a normal distribution problem where there's misspecification in the variance, but not in the mean part. And so what we can do is there's a way to see what is the sort of the quote right learning rate, which is the ratio of your positive variance to the true variance. And so we can plot this thing as a function of that ratio. And so at 1 is where the model is correctly specified, and to the left is where you've underspecified. So your positive variance is too small, so there's some risk of the miscalibration then. And so what you see here is that these are the 4 different methods that I mentioned before. Some of them are calibrated, so GPC is calibrated. I guess that's what it's designed to do. It's at least pretty close to this 95 range. The Leiden et al. Method is actually a bit conservative on in terms of calibration, but the others are a bit short, right? And so again, that's not surprising. These are not designed to be calibrated, but it still is I think is an interesting question. But at the correctly specified model, everybody does great, right? Okay, so you can obviously set up lots of different things. Recent review paper with a former student, what we tried to do was pick some reasonable models and try some different ways in which the model might be misspecified and see how things go. So this is not an exhaustive summary of the results in that paper, but I picked some that I thought were the comparisons are, most striking. So there's 2 ways in which the model can be misspecified, and it's only one of them is happening at a time. One is where it's a regression model. So the model assumes that its errors are Gaussian and constant variance. So what I've done here is I've introduced some cases where there's non-Gaussian errors, and then another case where there's some situation where the variance of the error terms is dependent on the covariate, right? So there's heteroscedasticity. So these are guess a few kind of summaries here, but what can happen is that, well, you might cover well in certain cases, there's other cases where you don't. And so just as an example is, this is a very extreme one, but in this particular case where there's some kind of heteroscedasticity, the Leiden et al. Method is very much not calibrated, right? Again, it's not what it was designed to do, but that's just what happens. But the one that is designed to be calibrated stays calibrated. That's, I think, is the important point. Right, so this is the paper that has those more extensive kind of comparisons of the different learning rate selection methods. Again, the takeaway here is that the thing that's supposed to be calibrated is the one that stays calibrated. Other ones sometimes are calibrated, sometimes they're not. Not a criticism, those are not designed to be calibrated, but I think it's still an interesting question. Now, again, my focus was on calibration. There are other metrics you could use to compare these things. And so, for example, like Grunwald's strategy, the safe-based strategy is, this one is intended to make posterior risk small. So if you try to do comparisons in terms of posterior risk, I would imagine that this one is going to be one of the better ones. So it's just a matter of the kind of priorities we have and different metrics we choose to compare. So I probably like just a couple minutes left. Is that right, Matthias? Okay. So I had, I guess, time permitting, I was going to talk about something. Maybe I'll just very briefly say something about this anytime validity. So this is something I was more recently interested in. There's lots of action going on with this kind of stuff. And so the main point here is that what's useful in these contexts is these things that they call e-values or e-processes. And so when dealing with model-based types of things, so focusing on likelihood ratios and stuff, what ends up happening is that these kind of the quote best of the e-values tend to be Bayes factors. So I was working on this, and so it's a little bit more than a conjecture. I just don't have the paper written yet. If you push this into something where questions are not about the model parameters or model density itself, but about risk minimizers, there's a way to see these kind of optimal e-values as what I'm calling here Gibbs factors. So again, when you have to deal then with these kind of what I'm calling here Gibbs factors, learning rates appear. And so I some related work with a current student talking about what we called here generalized universal inference. And so this brings in something like a likelihood ratio, but now it's this kind of the fake likelihood that we were talking, that I mentioned about earlier. And so this also requires specification of some kind of learning rate. And if we know it, everything's good. If we don't know it, then we need a data-driven solution. And so this some version of this calibration algorithm that I was describing actually surprisingly works quite well for these problems. Okay, so I'll just wrap things up, just a couple more slides here. So this is quoting myself, generalized Bayes is a liberated Bayes, right? I think that's maybe the thing I want people to take away from this. And so, this sort of normative aspect of Bayesian inference, I think is quite attractive. This was something that, from back when I was a student was the thing that I really wanted to be Bayesian because of this. But I think that, this need to be, dependent on model is quite a restriction. And so I think to break free from this, from working with models and the fully and correctly specified models, I think there's some really great opportunities here. And so I'm excited that there's a whole community that's interested in these kind of things. It doesn't come for free though. So like I was talking today about the scaling ambiguity, and that sort of necessitates this consideration of the learning rate choice. Lots of different ideas. These are kind of like matters of taste or matters of philosophy. I've pushed for this calibration, and then specifically choosing that learning rate in such a way that the calibration is achieved. Again, I think that's exciting developments in this area, and what I like is that you feel like this is really pushing boundaries. It's like really changing the way people think about problems, and so that I think is quite exciting. So thanks to the organizers for putting this together. I think this is a remarkable experience for all of us. Can't end here without saying some things about some possible open questions. So prediction is one thing that I didn't talk about here. I've done a little bit of work on this, but I know that there's Jeremias and some other folks here have some recent paper about this. And so maybe the prediction is settled and maybe they can comment on this perhaps. The computational aspect, at least in this calibration algorithm that I was talking about here, there's a challenge in terms of actually computing, doing those computations. It's doable, but there's for sure there's some improvements that could be made. And so I guess I'm wondering, I know Pierre has worked a lot on the variational approximations for Gibbs. Maybe there's ways to bring those variational approximations to the inside of the algorithm to speed things up hopefully without sacrificing the accuracy. Let me do a slightly different order here. So I've also done something, and I think there's some potential benefits to this, is about reverse engineering loss functions. So we might actually be able to deal with cases where the quantity of interest, we maybe wouldn't naturally think of it as a risk minimizer, but if we could reverse engineer a risk function or a loss function that corresponds to, or that makes that quantity of interest the risk minimizer, then there's a direct path to a Gibbs posterior solution to this. So this can be done in some cases and maybe more general than what I've done before. People have asked me this before, why not? Right. So right now I'm only working with a single learning rate parameter. And you could ask, well, why don't you bring in more learning rate parameters, right? For example, one for each dimension in the parameter, right? So this, I think, is something that I mean, it's a very natural question. It does require some deviation from those kind of first principles of the Gibbs posterior, where do they start with, right? So that optimization problem and bringing in the learning rate because of the scale ambiguity, right? That bringing in more learning rates means you have to change that kind of first principle setup. And so that I don't know how to do, but I think that could be interesting if there's ways to push this. I have a few other things here, but maybe it's not so important. So I'll stop here and just say thanks for your interest in this general area and your attention in this presentation. This is sort of an advertisement here. This is for a class that I taught a couple years back at NC State. This is not about the generalization of Bayesian inference that we're talking here, but it is about a generalization of Bayesian inference. And so if you're interested in this generally, maybe you could take a look. This is course videos and notes and all of those things are there if that's something you're interested in. But anyways, feel free to reach out, send me email if you have questions, or you can find the papers there on my website. So thanks.
Thank you so much, Ryan, for your talk. It was super, super interesting. We have a couple of minutes for a couple of questions. So I don't know if anyone has a question, just unmute yourself.
Can I start maybe just with
Yeah.
a very quick one? I'd just quite like to hear more, Ryan, if possible, about reverse engineering loss functions. If you could just give us a really quick overview. I haven't come across this before.
Okay, so at least the version that I have experience with is like this. Was interested in an image segmentation problem. So that basically means is that you are looking at essentially you have a panel and you see pixels, and the pixel intensity, you think that like on the inside of some boundary, you think that there's like a higher intensity on the outside, right? And so you see an image, and we've seen these like things for like MRIs, right? You would see the kind of the brain map there, right? You see an image of, say, a slice of the brain, and we can tell it's a brain because like on the outer part of the rounded edges, right, it's like a lighter gray, and on the inside it's a darker gray. But you might be interested in trying to estimate this boundary. So I think like some surgeons are interested in being able to do this to kind of pin down, is there an abnormality or something that's there? Because then they're going to go in with surgery to try to remove these sort of things. And so they're interested in estimating these boundaries say of brain images. Now, I had seen work where they were positing some kind of statistical model to pin down like what's the relationship between the pixel intensity and the boundary. And once you start bringing in statistical model, then there's questions about misspecification bias and things like this. And so what we tried to do there was trying to think of the succinct way to say it is we know the boundary of the image has a real world meaning, right? We can basically see it. So then the question is, could we formulate a loss function so that the image boundary is the minimizer of the expected loss? And our idea was something like a misclassification error. it ends up having a slightly different form. But the idea is that what we want is for the true image boundary to be the minimizer of the risk. The problem itself isn't defined in terms of risks and losses. But if you can create a loss function so that the quantity that you're trying to estimate is the risk minimizer, and what this amounts to doing is to show that the expectation of the loss that you constructed is equal to is minimized at the true thing you're trying to estimate. Right. So through this process, you could then avoid a type of model specification bias, which comes from assuming things about the distribution of the pixels, the pixel intensity inside and outside the boundaries, things like this. So the paper is a 2020 paper. It's also with my former student, Nick, in Annals.
Oh, that's cool. Thanks so much.
I think we have time for one more question. David, go ahead.
Yeah, thanks. Hi, Ryan. Thanks for the talk. Really, really interesting and cool to see that the calibration is in some sense so easy with only 100 or so measurements even.
Not easy.
But yeah, no, but in any case, but I was wondering sort of, because you started the presentation talking about sort of the struggle in Bayesian inference in some sense, when you have wrong models, and then it's challenging to write down meaningful price and then so on, and then that's one of your motivations to do post Bayes. And I just wanted to sort of come back to this question. Maybe I missed it, but sort of could you comment on sort of how this calibration helps you in addressing this question, or whether this was just like a general motivation and sort of this didn't necessarily sort of go towards addressing this? Sort of how do you solve this now?
Okay, well, I mean, I guess that's, I'm not sure if it goes in a circle or if it's just a path, but I think there's motivation for wanting to depart a bit from the Bayesian, the sort of traditional Bayesian perspective because of some rigidity. So you have to specify models and so forth, right? So what I think is an obstacle is that when the quantity of interest is not like a model parameter, so it doesn't even make sense to formulate this problem in terms of a model. Right. If we have a way to do this directly, so through the Gibbs posterior, for example. So in this construction, you don't need a model at all, right? It's not about whether a model is correct or not. You don't need it, right? So this gives you a way to directly go to inferences about the quantity of interest. So this saves you from introducing sort of unnecessary nuisance parameters and having to do the marginalization. So like an example of this is that Wasserman quote kind of continues, and he says, if you wanted to make inferences on a quantile as a Bayesian, what you would need to do technically is to have a prior distribution on the whole distribution and then marginalize down to the quantile. And so he's saying that this is, I guess, kind of wasted effort, because all you really cared about was the quantile. Why did you have to bring in all this extra stuff? So more than that is that you might actually have prior information available about the quantity of interest, but you would not know how to incorporate that into a prior for the whole distribution, right? What you would have to do in this sort of bigger kind of model-dependent case is probably just do some default prior for this parameter that you don't know what it means. And so that was a wasted opportunity, because like this is a quantity that you actually knew something about, but you just didn't, the machinery didn't allow you to incorporate this. Okay. So now if you kind of continue along this path, well, you get to a point now where when we break away from what the Bayesian framework says, now we can't count on these probabilities that we get out of this to mean anything, right? We really are just taking these pieces, putting them together, turning a crank, and it spits out a probability distribution. But there's no reason for us to think that these probabilities are real or reliable or anything. And you say, well, what could we do to try to make them real or reliable or something? And so my feeling was that this is where the calibration comes, is you say, well, I may not be able to make them real, but at least I can make them reliable, and reliable in a certain sense. And so then they can work for the things that we want them to be able to do. Whether they work for other things is a different question, but at least we can construct them in a way that work in terms of producing, I guess, this kind of reliable, let's say, credible regions. Right?
Thank you.
Great. I think we don't have time, so thank you all for coming, and thank you, Ryan, for the great talk. We'll see you all in 2 weeks.
Okay. Thank you, everyone. Thank you.